section 4.4, the mean value theorem. Before talking about the mean value theorem, we're going to talk about a more specific version of the mean value theorem, which is actually quite important for proving the mean value theorem, and that being Rolle's theorem. Rolle's theorem states, let f be a continuous function over a closed interval ab and differentiable over the open interval ab such that f of a equals f of b. Then there exists at least one c in ab such that f prime of c equals 0. What Rolle's theorem tells us is that if f satisfies all the conditions of Rolle's theorem, then f has a local extrema located within AB. The reason why Rolle's theorem holds can be shown through the pictures below. If we consider our points at A, f of A, and B, f of B, because of the conditions of Rolle's theorem that f of A equals f of B, the only way we can connect our lines with a continuous differentiable function is either with a horizontal line, in which case everywhere the derivative is 0, or from A, f of A, we're either increasing or decreasing, which we can see with all three pictures. The first and the last, as we start tracing our graph away from A, we can see our functions are decreasing. As for the other, in the middle, we're decreasing as we trace away from A. But since f of B is also equal to f of A, somewhere along our graph, due to continuity, we have to turn around in order for us to reconnect our graph to be f of B. When our graph turns, changing from increasing to decreasing or decreasing to increasing, that means our derivative is changing from positive to negative or negative to positive. Well, from what we discussed in the previous section, since our function is differentiable, meaning our derivative is continuous, then changing from positive to negative or negative to positive would indicate that our derivative would be 0 somewhere within the interval AB, which creates these local extrema. Now, keep in mind, Rolle's theorem states that there exists at least one local extrema. However, there can be multiple local extrema, as we see in the third graph. The primary use of Rolle's theorem is to prove what we call the mean value theorem. Mean value theorem states, let f be a continuous function over the closed interval AB and differentiable over the open interval AB. Then, there exists at least one point C in AB, such that f prime of C equals f of B minus f of A all over B minus A. Mean value theorem is a more general version of Rolle's theorem. The biggest difference between the conditions of the two theorems is that Rolle's theorem has the extra condition that f of A equals f of B. If we do add the condition that f of A equals f of B, then our numerator would become 0, meaning we would have the conclusion f prime of C equals 0, just like Rolle's theorem. So mean value theorem is just a generalization of Rolle's theorem. As for the interpretation of mean value theorem, the mean value theorem tells us that if f satisfies the conditions that we listed in the mean value theorem, then there is a point C in AB such that the tangent line of f at this point x equals C is parallel to the secant line of f that passes through our endpoints at x equals A and x equals B. And we can see that through our diagram on the right. Here we have the secant line that connects the points A, f of A, and B, f of B. And recall from our previous units, f of B minus f of A all over B minus A would be the slope of the secant line. Due to the conditions of mean value theorem, we can find at least one tangent line that will be parallel to the secant line, meaning the tangent line will have the same slope of the secant line. Now, to prove why this is true. To do this, we're going to use Rolle's theorem to help us. From what we talked about earlier, the f of B minus f of A all over B minus A represents the secant line of f of x passing through the points B and A. So what we can do is we can make an equation of our secant line. Since our slope of the secant line is f of B minus f of A over B minus A and passes through the point A, f of A, then the point slope form of our secant line is y minus f of A equals f of B minus f of A all over B minus A times x minus A. We'll add over B f of A, and we get that our secant line is y equals f of B minus f of A over B minus A times x minus A plus f of A. Since I'm trying to prove the mean value theorem, all I can assume is that our function is continuous on AB and is differentiable on AB. This is not enough to use Rolle's theorem. So what we need to do is construct a new function. We're going to let g of x be equal to our f of x minus the equation of our secant line. The reason why we wanted to find this new function is, first of all, because f of x is already continuous and differentiable on the closed and open intervals of AB respectively, and our secant line is a line which is continuous and differentiable everywhere, then g of x is going to be continuous on the closed interval AB and differentiable on the open interval AB. Furthermore, g of a would equal f of a minus f of B minus f of A over B minus A times A minus A plus f of A, which would simplify to 0, since A minus A is 0. Since g of A and g of B both equal 0, then all of the conditions of Rolle's theorem have been met. So by Rolle's theorem, we know that there's some c in AB where 0 will equal g prime of c. But g prime of c, if we take the derivative of our function and plug c into it, will be equal to f prime of c minus f of B minus f of A all over B minus A. Add over the slope of our secant line, and we get that this same value of c causes f prime of c to equal f of B minus f of A all over B minus A, which is precisely what we wanted to show. Now we're going to demonstrate through an example that the mean value theorem does work. We're going to let f of x equal 6 cube root of x plus 5. We're going to find the average or mean slope of f on the interval 0, 8. The phrase average or mean slope is another way of saying slope of the secant line. which would be f of 8 minus f of 0 over 8 minus 0. F of 8 is 17, while f of 0 is 5. 7 minus 5 is 12, while 8 minus 0 is 8, and we get that our average slope is 3/2. Next, we can clearly see that f of x is continuous everywhere. To see that it's differentiable on the open interval 0, 8, we'll take the derivative of our function, and we can see that f prime of x would be equal to 2 over the cube root of x squared. So from the derivative, we can see the only location where our function is non-differentiable is x equals 0. 0 is the bound of our closed interval. When we look at differentiability, we only consider the open interval. So indeed, f prime of x is differentiable on the open interval 0 to 8. So to summarize, f of x is continuous on the closed interval 0 to 8 and is differentiable on the open interval 0 to 8. So by the mean value theorem, we know that there exists a c in the interval 0 to 8 such that 2 over the cube root of c squared, which would be our derivative evaluated at c, equals 3/2. Now, usually when we're using mean value theorem, we would stop there because usually mean value theorem is used a lot like the intermediate value theorem in the sense that it just tells us something exists. But to demonstrate that this value of c does actually exist, let's solve this equation. To solve the equation, the first thing we should do is cross multiply, and we have 4 equals 3 cube root of c squared. Then we would divide by 4, then cube both sides, and then square root both sides. And we get that c would equal plus or minus 8 root 3 over 3. But remember, we're only looking for the value guaranteed by the mean value theorem. Since our interval was 0 to 8, then we would drop the negative value of c and only keep the c equals 8 root 3 over 3. So the value would be guaranteed for c by the mean value theorem is 8 root 3 over 3. Sometimes you can get more than one value of c. The mean value theorem tells us that there is at least one value of c that satisfies the conclusion, but here we only got one. Next, we're going to look at a problem where we can use the mean value theorem in a real-world situation. Suppose 2 stationary patrol cars are equipped with radar, are 5 miles apart on a highway that has a speed limit of 60 miles per hour. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit at some time during the 4 minutes. To help us understand the problem, let's start by drawing a picture. The blue line will be the road, and the 2 dots will be the location of our patrol cars. We know that the length of this road is 5 miles. We're going to let s of t be the distance between the truck and the first patrol car t hours after the truck passes it in miles. So by how we define our function, making our leftmost car the first patrol car, our first patrol car would be position 0 s of 0 or 0 0. As for our second patrol car on the far right, when our truck passes it, we know it's going to be 5 miles away. So we know s of something would have to equal 5. But what would be our time t in hours? We know the truck takes 4 minutes to pass the second patrol car. What is 4 minutes in hours? Well, recall there's 60 minutes in an hour. So 4 minutes would equal 4 over 60 hours, or a 15th of an hour. So the truck will take a 15th of an hour to travel from patrol car 1 to patrol car 2. The question is asking us if our car exceeded the speed limit. Since speed is part of velocity, we want to try to see if our velocity is greater than our speed limit. Recall, velocity is the derivative of position, and we always assume that position functions are continuous and differentiable. This gives me what I need to try to use the mean value theorem. By our mean value theorem, we have that there exists some c in this time interval where v of c is going to equal our average speed between the first patrol car and the second patrol car. If we plug in our values for s of 15 and s of 0 and work out the arithmetic, we get that the average velocity is 75 miles per hour. 75 miles per hour is greater than 60. So, thanks to the mean value theorem, we can conclude that at some point in time between the 2 patrol cars, the truck exceeded our speed limit of 60 miles per hour because somewhere it had to go 75 miles per hour. Could it have gone faster? Yes. But all we know for sure is that it did exceed our speed limit by at least 50 miles per hour.